Anybody have any questions or concerns, or want me to go faster, slower? Same speed. All right. This is really a useless slide. I got to say, I'm just going to skip it. But well, you know, so this is what you're doing when you do a parametric significance test. You take your observed value of some difference between, say in fMRI, say difference between signal values or whatever, and then you look at the variance associated with that difference, and using those two numbers, you can transform them into a t score, a t statistic, and then you look on this t distribution and you say, well, is the t-score that I observed, is it more than, is it past the 95% level on this? Does it lie to the right of 95% of this curve, or doesn't it? And if it does, then you remember that you should have corrected for multiple comparisons. Then you do it again, and then finally you report it. So when I talk about non-parametric statistics, which I'm not going to do much, but I do often find myself talking about permutation testing, which is a kind of non-parametric statistic. I'm really still talking about the same thing. It's actually just a different way to get this distribution. Instead of getting it from a table of t-values in the back of a statistics book, or actually in a stats program, you're using the data to generate this same null distribution. But in both cases, in both the parametric and the non-parametric statistics, for the most part, you're basically comparing the observed value to some estimate of what the distribution of values would look like if there were no effect whatsoever. It's the same for both. This is my slide about linear and nonlinear functions. I just dummied up some fake data to sort of explain this. But you can imagine now. I should say that this makes a little less sense in the context of VLSM than. In the context of voxel-wise VLSM than in the case of fMRI. But imagine you're looking at percent damage in some region and response time. So you can imagine a function like the one in the top left, where there's a linear relationship between percent damage and response time. So if the increase in response time associated with 5% damage is half the difference that you associate with 10% damage, and it's very easy to model the data. On the top right, you see a quadratic function, but only the right-hand side of the quadratic function, and maybe a little bit off to the side. So this is some sort of function that's like y equals x squared, something like that. And what you can see is that actually a linear model, so the line is a regression model, fits these data points. A linear model still does a pretty good job. So if this is the true state of affairs, if there really is a quadratic relationship between damage to this region and performance, then you would be able to detect it in this case. But it depends on how your experiment is calibrated and exactly where you sit on that curve. So on the bottom is a curve that has exactly the same shape, but we're shifted over a little bit. So it's again a typical quadratic function. It's a parabola facing upwards or pointing downwards. But the range that we're looking at is different. Actually, the range is the same, but I could have made it so the range was different. And now the regression is hopeless. Now the best regression line has no slope whatsoever, and you won't be able to detect this arrangement. So all of a sudden we've gone from two true states of the world that actually have in some ways the same relationship between damage and behavior. But in one case, a linear model is going to completely miss out on the effect. In one case, it's not. I don't have a lot more to say about that right now. And linear models have been problematic in a lot of this analysis. But it's worth considering that.
Just one second. Do you know in which cases for what kind of task usually you observe not linear relationship between percent damage and performance?
Well, there are some obvious ones where it's sort of forced to be nonlinear. So when you have error rates that are ceilinged, or response times tend to asymptote. So these things couldn't possibly be perfectly linear. But in I guess I can't think of any less obvious cases, but it could certainly depend on the psychometric qualities, properties of your test. Or
you had an intuition which model we should look at first when you have that type of data or something like that.
I mean, for a lot of people, I think it's an argument for looking at your data exploratorily, getting good pilot data.
Dan, how does I think you said it didn't, but this issue of linearity and the typical VLSM where you have just one of your variables is categorical or dichotomous rather than continuous.
But it's certainly less of a problem. I think it can be more of a problem if two of your variables are categorical, because then you might end up splitting your data in an unfortunate spot, and end up sort of mixing. Basically, say the natural division is like high performers and low performers has a cutoff that's not really in the middle, and if you aren't aware of that, you could end up having one group that's high performers and half the low performers, and another group that's all low performers, and you reduce the sensitivity of your test. But in general, I don't think it's a problem if you have the typical case in a VLSM where you have damage or no damage in each voxel. I think it can be a problem for multivariate methods when now you're integrating information from multiple voxels. Now all of a sudden there isn't just ones and zeros, but there's sets of ones and zeros. So in 2003, Bates and a bunch of colleagues coined the term voxel-based lesion symptom mapping, or VLSM. And even though I don't think it's perfectly descriptive, I think it's catchy enough, so I've tried to stick with it. Aside from the fact that it uses lesion data and not imaging, and the direction of causality is different, it's essentially the same thing as statistical parametric mapping. It's the same thing conceptually that you're doing in fMRI, in that you're carrying out a parametric statistical test in each voxel and mapping it to that location of the brain, carrying out a significance test in each voxel using that data. And I sort of believe that part of the motivation for doing this was to sort of leverage all the wonderful things that fMRI analysis can do in the service of VLSM. And part of it might have been some jealousy at the cool figures, because lesion figures were never this cool before 2003. I don't want to make too much of that, but it does keep coming up. And compared with typical overlap mapping, it's statistical, and it's compared with the methods for categorizing patients. It can in principle be as fine-grained as your lesion maps are, if that's really what you want. Doesn't follow that that's a good idea, but it can be. Now, there's a corollary to this, which is that for any increase in resolution, you also incur a potentially expensive correction for multiple comparisons. As you move from 10,000 to 20,000 voxels, it doesn't get worse as fast as it did from 2 to 10, but still, it's more comparisons for no good reason is not a great idea for power. And the other advance that I sort of associated with this article was really a focus on continuous measures for behavior, even though they didn't invent that. So going back to...
I just wanted to say that for me, the most revolutionary thing about this was the size of the groups. And I mean, this is something that you should be aware of, right? In that there's been a kind of almost quantum jump in the group size. So Bates et al. Reported 100 patients or perhaps more, right, in their analysis. And this was essentially unheard of prior to this time in lesion mapping studies. The reason that they were able to do that is because they reported that in that paper they looked at a basic screening test for aphasia, a performance on a Western aphasia battery test, and so it wasn't an experimental paper, right? So if you are actually doing experimental lesion analysis, and you have to build up, we're going to talk about the importance, right, of power here and having sufficiently large groups. This is a major sort of change in thinking, almost revolutionary, really, in lesion studies.
I would say to some extent it's forced people. My impression is that people who've done lesion studies even before VLSM paid less attention to power than they should have. I guess that's true of all areas of research. VLSM has definitely forced more of a focus on power because it does place more demands on your data. This is the same data set that Rorgan and Carnath reported in those 3 rows of overlap maps that I showed earlier. And now done with proper statistics. In this case, it's a chi-squared test that they carried out using the using something that's basically the same thing as VLSM. They called it. They're trying to call it something else. I won't even say what it is. They had a different abbreviation. You can see that it yields an area that's much more readily identified with visual field defects. And in fact, some patterns that were evident on the overlap difference map, which seemed to be just as hot as these posterior regions, turned out not to reach significance by this test. Anyway, so to me, I sort of summarize this lesson as that it's important to ask the right question. And that VLSM isn't so much a completely different technique, but more a technique that encourages you to ask more incisive questions. That might not be completely true, but I'll say it anyway. So as part of my mission to make VLSM as non-mysterious as possible, I'm going to tell you how to carry out a VLSM analysis without computers, by hand. And it's actually really, really easy. Well, parts of it are easy. So step one is to pick a template, because you want to make sure that when you're comparing whatever it is, the anterior pole of the hippocampus or whatever, from one subject to another, you're getting the same area by some measure. So pick a template, and in many cases we pick the brain of Colin Holmes, who was scanned 27 times and is now the proud template for all imagers everywhere. And then place a push pin on the first voxel just to make sure you don't lose your place. And I guess you can go in whatever order you want, but you want to make sure that you're eventually going to be able to get all the voxels. And then go through the MRI scans or whatever you have, CT scans of all the patients you have, and eyeball it to see if the voxel is intact or damaged in that subject. So hold the column brain over here and hold your subject's MRI scans over here, or you can put them up on the wall, and look back and forth and try to say, does this location look like it's damaged in this patient? And then write that patient's behavioral score down on a slip of paper. And if you decide that voxel is damaged, you put it in one bucket. And if you decide it's not damaged, you put it in the other bucket. And you repeat that for all your subjects. And then, I'm not sure how to do this without a computer, but I mean, I know how to. But if you don't have that too many subjects, you can carry out the t-test by hand with those slips of paper. So now you have a t-score associated with that voxel. Okay, so it's really easy. I mean, it would take a lot of time, and you'd probably make arithmetic errors carrying out the t-test, but it's not conceptually very difficult. Then you move the push pin, you do the next voxel, and you keep repeating steps 3 through 5 till you've gone through the whole brain. Once you've gone through the whole brain, you have a t-score for each. I guess I could have added some more items at the bottom. Now you have a t-score for each voxel in the brain. And when I say voxel, I mean place where you put the push pin on the template. And you could, if you had a small enough paintbrush, assign a color to different ranges of the t-test and color in that column brain. And if you're clever enough, you can correct those colors for multiple comparisons, which really isn't that difficult, because all you need to do is look up your t-values on a t-table and correct the p values. So VLSM is easy. Now, I'm not saying that this is exactly appropriate for every VLSM analysis, or that there aren't little complications that get thrown in, but this is basically what we're doing. And the only tricky part is that we have lots of software that makes this a lot easier, and we want to make that software as easy to use as possible, but it isn't always. And sometimes the software does things that you don't expect.